Hey everybody. Today we're talking about the variance and standard deviation of continuous random variables. Basically, talking about the spread of those random variables. The definitions are pretty much identical to the definitions in the discrete case, except we've replaced the summations with integrals. In these equations that you're seeing here, S is the support of the random variable x, mu is the expected value, or mean, and little f of x is the probability density function. So I guess that's another small difference in the discrete versus continuous case. Here we have a density function instead of a mass function. When you're computing variance and standard deviation directly from the definitions, things can get ugly. So it's almost always easier to use an alternative formulation that the variance of a random variable is the expected value of x squared minus the expected value of x quantity squared. I've put the proof here. It just uses the linearity of expectations, and the proof is exactly the same whether we're in the discrete or continuous case. Let's jump in with an example. Find the mean, variance, and standard deviation of a random variable that has a uniform distribution on the interval a, b. As usual, I recommend pausing the video here, trying this problem on your own before seeing my solutions. So first of all, notice that the probability density function here has to be 1 over b minus a. We have a constant density function on an interval of width b minus a, so the height of that density function, the height of this rectangle, has to be 1 over b minus a. Let's use that to find the expected value, the mean of this random variable. And that just means integrating over the support, so from a to b, x f of x dx. So that's x over b minus a. The 1 over b minus a factors out. We're just integrating x. That's 1 half x squared. We plug in our endpoints, simplify a little bit, and we get 1 half b minus a. And that makes sense. That's just the interval of the midpoint of the interval from a to b. Next, we're going to find the expected value of x squared, and we need that in order to apply the formula for the variance of x. That means we're integrating x squared f of x over the support, so the integral from a to b, x squared over b minus a dx. Once again, we factor out the 1 over b minus a, integrate x squared, plug in the endpoints. Overall, we get 1/3 times b squared plus ab plus a squared. All right, so let's apply that formula for variance. The expected value of x squared minus the expected value of x quantity squared. We plug in the things we got, do a little bit of arithmetic, a little bit of simplifying. We get 1/12 b minus a quantity squared. So that's the variance. Of course, the standard deviation is the square root of that, b minus a over the square root of 12. So here in this formula, as in the previous ones, we're assuming that b is greater than a. Now, neither variance nor standard deviation are linear operators, but they both have some properties that are really helpful for sums and constant multiples that are sort of reminiscent of linearity properties. When x and y are independent random variables and little c is a constant, the variance of a constant times x is the square of the constant times the variance of x. And the variance of a sum, x plus y, is the sum of the variances, variance of x plus the variance of y. Now, it's important to note that that second property only holds when you have independence. If x and y are dependent on one another, then the formula for the variance of a sum is more complicated. The formulations for standard deviation are basically just the square roots of what we saw before. So if you need the standard deviation of a constant times a random variable, you take the constant times the standard deviation of the random variable. But since standard deviation is always positive, we're actually factoring out the absolute value of c. Additionally, the standard deviation of a sum is the square root of the squares, rather the sum of the squares of the individual variances. And again, that latter formula only holds when the random variables are independent of one another. By the way, notice that that second one is basically a Pythagorean theorem. That's an interesting thing to ponder on your own. All of these identities are proved directly just from the definitions of variance and standard deviation for continuous random variables. Let's do one more example before we wrap up this vid. Compute the variance and standard deviation of a random variable x with this density function. It's going to have support from 0 to 2, and on that support, the PDF is going to be 1 minus 1/2 x. Once again, Pause the video, try this on your own before seeing my solution. So first we're going to find the expected value of x, then we'll find the expected value of x squared, and that'll get us the variance as well as the expected value. Again, we're integrating x f of x over the support, so from 0 to 2, x times 1 minus 1/2 x. We do out that definite integral. Overall, we get an expected value of 2/3. So even though this random variable can take values from 0 to 2, on average, we expect to get 2/3, which is sort of less than the midpoint of that interval. Similarly, we calculate the expected value of x squared by integrating from 0 to 2 x squared f of x dx. We do out that arithmetic, we once again get 2/3. It's a little bit of a coincidence that the expected value of x squared and the expected value of x are the same in this case. Plugging into that variance formula, doing the expected value of x squared minus the expected value of x quantity squared, we're doing 2/3 minus 4/9. Overall, that's 2/9. So the standard deviation of this random variable is the square root of 2 over 3.